Okay, so today's video is going to be about, I'm going to, sorry, yeah. So today's video is going to be about quantum mechanics. So, sorry, let's start with, because let's have a difference. Let's talk about difference. Difference between classical physics and quantum physics, because most of the time in what do you call this, in physics, most of the classical physics is, because common people know classical physics. Okay, by common people it means that people, because classical physics is what, it's about everyday life, right? Everyday life. So the questions you will ask about everyday life will involve physics. Like, let's suppose you will ask a certain common person, why am I drawing him big, a person, let's suppose then one who is like new to science. You ask him that if I have a ball, okay, if he has a ball and he throws it up, so and then he asks what will happen next, what will happen next. So what do you think he will answer? He'll say, of course the ball will come down, right? The ball will come down, and if there's nothing in like under it, it will fall to the ground. Okay, so this everyone knows, but let's suppose you ask the same person that what will happen, what will happen if electron or a particle, quantum particle, is thrown. What will be his answer? Of course, again he will say the same thing. Even though it's a particle or whatever it is, it still looks like a ball, right? So what he will say is that he will give the same answer. He will say return back sorry return back again, back again. So, but we, those who study quantum mechanics, know that it's wrong. That doesn't happen, because in quantum mechanics, what, first of all, over here, when you talk about ball going up and down, or let's take another scenario, the ball is, for simplicity, the ball is moving in x-axis. So if this is its for first, let's suppose it's x1, or not x1, yeah, this is x1. We know that particle is here at this point. Okay, it's over here. After it moves certain distance, it will be over here, right? So this is a distance covers. If we draw it in a graph, in graph means we involve time. So it will be in while graph, what will it be? It will be a speed time graph, sorry, distance time graph, distance and time. So if we know that sorry, Let me just draw this. So let's suppose if the ball is here, so after certain time it will travel a certain distance, right? It will go like this and it will reach here. So how can we know its position? Its position is from here and here. We know that this is its path. This is the path taken. Path taken. Now this is a little advanced physics, not that hard, but still lower than quantum physics. This is what, like, this is a graph. I showed in a graph, but the normal what I want to show is, or what I want to say is that we are able to predict. Prediction can be made that where the ball will be at time final. Okay, but you will not get the same answer, but let me write a big one, but you will not get the same answer if we do the same thing with quantum particle. Let me tell why. Because according to quantum mechanics, when you have, let's suppose this ball, quantum particle, okay, you have, why his hands are connected with his legs. Okay, so he has a quantum ball and he throws it up in the air. Now after he threw, he only knows its final position, and he only knows its initial position, final position, and this is initial x, final x. Okay, so what he knows is that where he, from the point he threw, the point when he will measure. Now let's get to the main quantum mechanics. Now after he will measure, let's suppose this is the point when he measured. So the path in between, that path, to know that path, we have to, you will not believe me, but to get the exact path, or to get that path, we have to consider all the paths which can be in between. Whatever, consider each and every path there possibly could be. Okay, again, vi, vf, xi, x, this. So we have to consider each and every possible path, and then do what? We do summation of all all of the paths. Just by talking about this, I came across a new topic known as, this is Feynman's perspective. It's known as path integral. This is what, just because it's in this, so we will add it. Integral path. It's not that, like, it's one of the things we discover. Okay, so we call it path integral. What? This one. Wait, sorry, let me get to the lines. This is what path integral is. path integral is discovered by Feynman, saying that if we have a quantum particle and we want to know its path, we have to consider each and every single path that particle could take place could take. Sorry, pardon. So the formula, let me just give the formula, then we will talk about it. The formula is E summation of E to the power I S over ST. This is the same as saying summation of E to the power I of this. This is also symbol. This symbol is same as saying S over this. Okay. So I'll tell you what this means just now after we talk about one of the famous experiments in the quantum world or quantum realm. I will not call it quantum world, I will call it quantum realm. Quantum realm. Quantum realm. Okay, because it makes it a little like fascinating. So one of the biggest experiment in quantum mechanics, Young's double slit experiment. Young's double slit experiment. Okay, now we all know what Young's double slit experiment is, right? We have an electron gun which passes electron in waveform, and it goes through the let me change color. It goes through the not like this. It goes through slits. After it goes to the first slit, it will spread out. Then we have two slits. So what will happen in that? Again it will go back, again it will split, same thing will happen. Now we have two slits. Now wherever the slits are interfering, let me just make a graph, how the wave graph, how it would look like. So we could say that this point and all the points here, we say that the probability of finding them at the borders is less than the probability of finding them in the top, the most highest one. Okay, and this is taken when you take a square of the wave function. Okay, this is called density, probability density. Okay, so then here the key point I want to show is that let's suppose we know that when we are not observing it, when we are not observing the particle, it will go this and then back this, maybe then we can this, and whatever we have, let's suppose it could be done here. So what I want to say is that it will take one of the paths, right? It will take over here, it will not take one path. So imagine we do the same thing, but we add so many of the slits. Okay, we are adding so many slits that look, we had so many slits, where the holes in them with not slit, so many parallel lines, barriers which have many slits, and now electron gun will take all the possible paths, right? Because that's what the integral is about, path integral. Taking in account also the one who will calculate all this has to take all the possible paths to get exact whatever we want, exact position, exact path taken. So what is observed is that, let's suppose we make these slits so small, make slits so small that they disappear. Now when they will disappear, there will be nothing, right? So this is what you will observe. Right, look, this is what you will observe, right? It's the same as over here. It's similar, right? This is similar, they both are similar. All of them are similar. What do you say? Similar, sorry, similar. So one more thing, this integral, sorry, e to the power I, this is what, nothing but the distance between from here till here, no, not here, from here till here, this is what that is. Okay, so let's just talk about E. Well, this is what the path should look like when you display all of the barriers which have, you make so many hit slits that will disappear. It's the same as saying for a Huygens principle, in which you are taking in each wave, you're taking so many small ethers that they themselves again expand and make the new wave. That's the same as in that we added, in this we remove. Okay, so sorry, not I to the power. In this S is the integration, is the Lagrangian, or is also known as action done. In Lagrangian, it's taken as k minus u. In full glory, it will be integral of dx infinity to the power negative infinity to infinity dx k minus u equal 1, normalization. This is what? Action. Okay, I think this color may not be visible, so let me just redraw. K minus u integration d of x, normalization 1. Why do we normalize? We normalize to get a physical quantity. So this is k minus u is the Lagrangian. We already talked about what Lagrangian is before in the videos. So, and I is the complex number, h bar is for size. You might have noticed, if we talk about the size h bar, what is h bar? H bar is 6.63 times 10 to the power minus 34, right? Almost so small. It's very small. It's like less than atom, the smallest scale possible. So you would say that if we take this for a tennis ball, the value the value the value will be small, so small, right? But if for macro, but for micro it would be huge, because the mass of electrons, the size of electrons, because electron size is less. Okay, and so is that it, or is there something else? I think, yeah, that's it. Yeah, that's it. Thank you.